In part 2 of the videos over section 6.2, we take a look at what are called vector line integrals. These are somewhat different from scalar line integrals in that the integrand will contain a vector valued function instead of a scalar valued function, f of xy or f of xyz. In fact, what we're going to find is that we're often going to compute these in vector fields, and the vector field will be a part of the integrand. Now, when we do this, we need to consider that we're going to have an orientation. Vectors have a direction, so it makes sense that this time when we compute a vector line integral, that we'll have to indicate which direction we're traveling along our curve. This was not necessary with scalar line integrals because the scalar line integral gave us the area of the drop curtain, which was always non-negative. However, as we're going to discover, vector line integrals can be used to compute the work done by a force in moving a particle from one point to another point along a particular path. In this case, if we think of it as work done, the direction of travel makes a difference. For example, if you're at base camp and you hike to the summit of the mountain, the effect of gravity is negative work. If you're coming back down, then the effect of gravity would give positive work. So while the absolute value is the same, the work done depends on whether you're traveling up against gravity or down with gravity. We're going to call this the orientation of the curve. And as in the example with gravity, we'll find that moving in the opposite direction of the curve will give us the negative of the value of the vector line integral. As part of our work in this particular part, we're going to be looking at what's called flux. Flux is the tendency for a fluid in a vector field where the vector field represents velocity of the fluid for it to pass over the curve as opposed to along the curve. If it is a closed loop, then we call it the circulation when it goes along the curve following the path of the curve. But when it moves across the curve at a right angle, then we call it the flux. Both flux and circulation are important in some of the later sections of this chapter. We'll see them again. Let me share my screen with you and we can get started. To motivate our work with vector line integrals, we want to think about having a continuous vector field, F, in R3 that represents a force being applied to a particle. And we want to think about a smooth curve, which is in the domain of our vector field. We want to think about how we could compute the work done by the force on the particle as we move it along the curve C. Now, since the particle could move in two directions along the curve, again, we could have it flowing from point A to point B or from point B to point A. We'll need to specify which direction we're traveling in. The specified direction will be called the orientation of the curve. We will have standard orientations later in this chapter when we're looking at particular types of curves. For now, we'll simply call it an oriented curve if there's a direction to it. For example, this becomes an oriented curve that flows from A towards B when I add the orientation arrows onto it. Let's think about how we can actually make this more precise. The first thing we want to do is we want to consider what we call a closed curve. When we study vector line integrals to define the circulation, the tendency for the flow to move along the curve in a closed loop, we have a closed curve. A closed curve is one where there exists a parameterization such that R of A equals R of B when T varies between A and B. In other words, a closed curve is one where you end up back where you started. Let's take a look at two examples of curves. In the example on the left, you see an oriented curve with an arrow along it moving from the point on the left to the point on the right. It's not a closed curve because T of at A gives us the location on the left, and T equal to B gives us the location on the right. And R of A does not equal R of B. However, in the curve on the right, we have a closed curve because wherever our initial point is when T equals A, when T equals B, we end up back at the exact same point. In other words, we could consider this point here to be when T equals A and T equals B. It's both the beginning location and the ending location. We both begin the loop and end the loop in the same location. And that makes this a closed curve. So how are we going to deal with these curves, whether it's an oriented curve that's not closed or it's an oriented curve that is closed? We're going to do essentially what we've done in the past. The calculus thing is to cut the curve up into tiny little pieces. So if you see the curve down here, you can see that it has been cut up so that you go from point 1 to point 2 to point 3 to point 4 along the curve. This subdivides it into subsegments of the curve. Then we're going to pick our favorite parameter value, T sub I star. And at T sub I star, we're going to compute our point, P sub I star, which is inside of the subdivisions. P sub I star, notice, is here in the ith subdivision of this curve, from P sub I minus 1 to P sub I. P sub I star is the point at which we want to evaluate the parameterization of the curve. R of T sub I star gives us P of I star. If we make our arc length pieces short enough, small enough, close enough together, they become nearly linear. And this is because it is, of course, continuous. Then we can say that the particle is moving approximately in the direction of the unit tangent vector at the point P sub I star. Let's take a look now at this picture and imagine, if we will, that we made an even smaller division so that it was even smaller between our two values. What we're saying is if you make the division small enough, it becomes so nearly linear that we could say that you're practically moving in the direction of the unit tangent vector at the location of P sub I star. How does this help us to find the work done? Well, if you'll recall, work is force applied through a distance. Work itself is not a vector valued function. It is, however, the dot product of two vector valued functions, the force and the distance. If we take the dot product of these two, we get the amount of work done on that small segment. So how much work is done on a very small cut of that curve? We can evaluate and assume that the force is roughly constant on a very tiny section if we evaluate it at P sub I star. So the force given by the vector field at P sub I star gives us that measure. And then we need to multiply it by the distance moved. If we look at the previous picture, the distance moved is this small little section that you see here. That small little section is basically the change in the arc length multiplied in the direction of the tangent vector. This means that we can compute the distance as delta S sub I, the change in the arc length, multiplied by the tangent vector at p sub I star. It's that length that was nearly linear. Of course, once we're done with evaluating the force on a tiny subsection of the curve, we're going to take a Riemann sum across all of the cut up pieces of the curve. We're going to add them all together and do the calculus thing, which is to take the limit as the number of subdivisions goes to infinity. The total work done along the curve can be approximated then by the Riemann sum of the vector field F evaluated at p sub I star in each subsection of the curve, dot product with delta S sub I times the unit tangent vector at p sub I star. If we do this for all of them and then take the limit, we will be able to find the actual value of the work done. In a sense, then, delta S sub I becomes our arc length differential ds. And we take the vector field F and dot it with the unit tangent vector. This gives us the work done along the curve in moving the particle from one end of the curve to the other in a particular direction. This leads to the concept of the vector line integral. The vector line integral of a vector field F along an oriented smooth curve is given by the limit as n goes to infinity of that Riemann sum. This is the small amount of work done if it's in a force field on each little cut, allowing the width of each cut to go to 0 and the number of cuts to go to infinity. Now remember, with a scalar line integral, neither the orientation nor the parameterization of the curve made any difference. As long as the curve was traversed exactly one time by the parameterization, the value of the scalar line integral is unchanged. In this case, however, with vector line integrals, the orientation does matter. If you move in the opposite direction along the curve, you get the opposite value of the vector line integral. Again, this should make sense if you think about the example of hiking up a mountain with negative work and down a mountain with positive work. Let's go ahead and now think about how we could possibly integrate this particular integral. The problem is that we've got the vector field dotted with the unit tangent vector and the arc length differential. Just as in the case of the scalar line integral, we really don't want to have to integrate with respect to the arc length differential ds. What we're going to do instead is convert each of the pieces into another valuation, which is in terms of the parameter t, much as we did with the scalar line integral. We're going to start with the unit tangent vector along the curve. Recall that a tangent vector is the derivative of the parameterization r prime of t. But that, of course, is generally speaking not a unit vector. To force it to be a unit vector, we divide it by its magnitude. We know that r prime of t is not the zero vector because it is a smooth curve. And that's part of the definition of a smooth curve. Since the arc length differential, ds, we found previously when we were looking at scalar line integrals to be the magnitude of r prime of t multiplied by the differential dt, we can replace these in our integrand for the vector line integral. The vector line integral on a curve-oriented smooth curve C is f dot t ds. We replace the t ds with r prime of t divided by its magnitude and ds with r prime of t dt. then the r prime of t magnitudes will cancel. And so for t ds, we get r prime of t dt. This representation right here is replacing the unit tangent vector multiplied by the arc length differential. Then we replace the vector field with f of r of t. And this gives us the representation of the vector line integral in a computable form. We go from the parameter value t equal a to t equal b of the single integral of f of r of t dotted with r prime of t dt. Remember that r prime of t is still a vector, so we have to use a dot product. Let's now go ahead and think about this new representation of the vector line integral. Since we had the integral of f dot t ds, and we rewrote this in terms of the parameter t from a to b of f of r of t dotted with r prime of t dt, we could, in a sense, define a new differential as dr, and we can call this the vector differential. When we're looking at it, r prime of t dt is replacing the ds that was there previously, but it is in fact still part of a vector. So we can use a vector notation to indicate that by writing it as dr with the harpoon over the r. Let's see how to apply this in example 5. We want to be able to compute f dot t, the vector field dotted with the unit tangent vector with respect to the arc length differential, by instead computing f dot dr, the vector differential. In this case, c is the curve with the parameterization t squared for t between 0 and 2. The vector field is given as x, y. In this case, we need to first parameterize the vector field. In other words, we need to find a representation for f of r of t. When we look at this, r of t is t squared. So we replace x with t and y with t squared. This gives us the representation for f of r of t squared. Now we need to convert that unit tangent vector with the arc length differential into r prime of t dt, which is also our dr, the vector differential. In this case, we need to go ahead and compute r prime of t. R of t is t squared, which tells us then that we can take the derivative with respect to t, and we should come up with r prime equal to 1, 2t. When we attach the differential dt to it, we can replace the unit tangent vector times the arc length differential with 1, 2t dt. The next thing we need to do is compute the dot product for f dot dr, or f of r of t dotted with r prime of t dt. This is another way of representing the same thing. Once we have this, we'll be able to do the integral. In this case, f of r of t is t squared. R prime of t dt is 1, 2t dt. And when we take the dot product of the two vectors, we get t plus 2t cubed, with the dt along as a factor. Now we're ready to integrate, and this time we integrate along t equal to a to b, which in our case is 0 to 2. When we plug in the parts, we get the single integral from t equals 0 to t equal 2 of 2 plus 2t cubed dt. We integrate with respect to t to get t squared over 2 plus 2t to the fourth over 4, and evaluating between 0 and 2 gives us the value of 10. If F represented some kind of force field, this would be the amount of work done in moving it from one point to the other along this curve. There is a second notation that we can use for vector line integrals that you may see in some textbooks and some applications on the internet. We start with representing the vector field in the form of P of XYZ in the I hat direction, Q of XYZ in the J hat direction, plus R of XYZ in the K hat direction. In other words, we can simply represent our vector field in terms of scalar valued functions, each appearing in its appropriate position in the vector which represents the vector field. If we only have something in 2 dimensions, then we would only have P and Q. Now, we can parameterize the curve C as well, and we can parameterize the curve instead as the vector x as a function of t, y as a function of t, and z as a function of t. Or again, if we're in 2 dimensions, x as a function of t, y as a function of t. Again, representing this as a vector valued function. Then we can represent the derivative of r of t as x prime of t, comma, y prime of t, comma, z prime of t, or dx dt, comma, dy dt, comma, dz dt. If we're thinking about this then, when we rewrite the vector differential dr as the unit tangent vector with the arc length differential ds as r prime of t dt, we take r prime of t, which is dx dt, dy dt, dz dt, and multiply by dt. Well, okay, they're really operations. They're not fractions, and this shouldn't work, but it does. They sort of, okay, I can't say it. They don't cancel, but you do get dx, dy, dz. And then when you dot this with the representation for your vector field, you'll get p dx plus q dy plus r dz. Once you have it in this form, however, you're not able to evaluate it on the closed curve until you re-represent it in terms of the parameter t. To do that, you in a sense kind of go backwards to thinking of r prime of t dt as dx dt, dy dt, and dz dt. Then you parameterize each component of the vector field, p of r of t dx dt, plus q of r of t dy dt, plus capital R of r of t dz dt, all then multiplied by the differential dt. And we can see this as well in the 2-dimensional case. Let's go ahead and pause here to go back to the previous example and apply this second notation to the work we did there to see how it does, in fact, give us the same result. In our previous example, the vector field was given to be x, comma, y. That means P is equal to x and Q is equal to y. Let's go ahead and make note of that now. P equals x, Q equals y. We were also told that the parameterization R of t was equal to t squared. The next thing that we want to do is evaluate P at the parameterization. Since the x component of the parameterization is t, then P equal to x becomes t. This then gives us the integral from 0 to 2 of t times dx dt. However, our x of t is, well, t, since this represents the parameterization. This is x of t right here. That means that the derivative is 1. And then we add to that q of r of t. Q is the variable y, but y is t squared. So we get plus t squared multiplied by the derivative of y with respect to t. But y of t from the parameterization is t squared, and the derivative would be 2t. Finally, we take all of this and multiply by the differential dt, and we integrate from t equals 0 to t equal 2. When we do this, do you see that you get exactly the same single integral as you got computing it with f of r of t dotted with r prime of t dt? Let's go ahead now and take a look at the next definition, which is, or actually, let's go ahead and apply this to another example, in example 6. Then we'll move on to the next definition. In example 6, we're given a vector line integral over an oriented curve C parameterized by 4 cosine of 2t, 2 sine of 2t, comma 3, t from 0 to pi over 4. This represents part of an ellipse in the plane where z is 3. When we look at this one, we're not given the actual vector field, but it's there. It's hiding in the integrand. What we have up here is p dx plus q dy plus r dz. We're going to need to convert this into the other representation, p of r of t times dx dt, plus q of r of t times dy dt, plus r of r of t times dz dt. Then we'll integrate on the t parameter between 0 and pi over 4. The first thing we need to do, of course, is identify our p, q, and r. P in this case is 4x, q becomes z, and capital R becomes 4y squared. Our actual vector field is given by 4x, comma z, comma 4y squared. We don't actually need the vector field to use this notation, but again, if you wanted to do f of r of t dotted with r prime of t, you would want the vector field. Now that we have p, q, and r, we want to evaluate p of r of t, q of r of t, and r of r of t, which basically means we are finding the vector field evaluated at the parameterization, f of r of t. In order to do this, we're going to go ahead and represent it in its vector form, f of r of t, which will give us p of r of t, comma q of r of t, comma capital R of r of t. P is 4 times x, so we have 4 times the x component of the parameterization. We also have a y component of the parameterization and a z component of the parameterization. Our x component is 4 cosine of 2t. This means that p of r of t is 16 cosine of 2t. Let's go ahead and take a look at finding q of r of t. Q of r of t, well, q is just z, and the z component up here is simply 3. That gives us our middle component, which just becomes 3. Our last component of f of r of t is found by taking the representation for r, which is 4y squared, and substituting what y is in the parameterization. In this case, we're going to have 4 times something squared, and the something squared is going to be the y of t, which is 2 sine of 2t. When we rewrite this, we're going to get 2 squared becoming 4 times 4 gives us 16. And then we'll have sine squared of 2t. This means that we now have p of r of t, q of r of t, and r of r of t, where p of r of t is 16 cosine of 2t, q of r of t is 3, and capital R of r of t is equal to 16 sine squared of 2t. The next step is to identify the derivatives. The derivatives refer to the parameterization, where the parameterization is x of t, y of t, z of t, and given by 4 cosine of 2t, comma 2 sine of 2t, comma 3. dx dt, of course, is the 4 cosine of 2t. To find dx dt, we take the derivative of that to get negative 8 sine of 2t. To find dy dt, we're going to take the derivative of 2 sine of 2t, which will give us that dy dt is equal to 4 cosine of 2t. And finally, to find dz dt, we take the derivative of the 3, which of course is going to give us a derivative of 0. Now that we have completed the parts, it's time to form the integral and evaluate. P of r of t turned out to be 16 cosine of 2t, and it gets multiplied by dx dt, which is equal to negative 8 sine of 2t. This is our P of r of t and our dx dt. We're going to integrate this one from t equal to 0 to t equal pi over 4. That gives us the first term, but we have 2 more to go. Q of r of t is equal to 3 times dy dt, which is 4 cosine of 2t. Finally, we take r of t, which is 16 sine squared of 2t, and we multiply this by dz dt, which is 0, which is rather nice because then the sine squared part will drop out. Let's go ahead and represent this in its final form. This is going to give us the integral from 0 to pi over 4 of what is 16 times negative 8? 128. Negative 128 cosine of 2t sine of 2t plus 12 cosine of 2t, all evaluated with respect to the t differential. Go ahead and pause the video to work out the integral, then turn it back on and we'll compare our results. In order to integrate, we want to split this into 2 separate integrals. For the one on the left, I went ahead and did a u substitution where I let u be sine of 2t. Then using the chain rule, I found that du is 2 cosine of 2t dt. I borrowed a 2 from the negative 128, which left it at negative 64. Then I substituted the limits of integration. When t equals 0, the sign of 2 times 0 is still 0. When t equals pi over 4, we have the sign of 2 times pi over 4, which is pi over 2, and sine of pi over 2 is 1. This changes the limits of integration from t equals 0 to t equal pi over 4 to u equals 0 to u equal 1 of negative 64 u du. In the next step, I integrated to get negative 64 u squared divided by 2 evaluated from 0 to 1. Negative 64 divided by 2 is negative 32, and substituting in the limits of integration gives me 1. This gives me negative 32 for the first term in the original vector line integral. When I look at the second one, I went and did a u substitution, but this time u was 2t. Then du is 2 dt. And again, I borrowed 2 from the 12, leaving it as a value of 6. Then I changed the limits of integration from t values to u values, finding that when t is 0, u is 0, and when t is pi over 4, u becomes pi over 2. This gives me the integral from 0 to pi over 2 of 6 cosine of u du. The integral of cosine of u is sine of u, and then I evaluate between 0 and pi over 2 to get 6 for the second integral. Negative 32 plus 6 gives me negative 26 for the value of the vector line integral. Let's now take a look at what a piecewise smooth curve is before we take a look at more of the properties of vector line integrals. What if your curve is not completely smooth, but it has some locations where r prime of t might be the 0 vector or not exist? That is, what if you've got corners or cusps in your curve? As long as you have a finite number of places where you have a corner or a cusp, you can break it up into what we would call a piecewise smooth curve, meaning that it's smooth on PC1, smooth on PC2, smooth on PC3, and smooth on PC4, but not smooth at the place where C1 meets C2, C2 meets C3, and C3 meets C4. We can find the value of a vector line integral much the same way we would do with a scalar line integral. We evaluate the vector line integral on each of the piecewise smooth pieces and add the results together. Let's go ahead and find the properties of vector line integrals. We're going to suppose we have two continuous vector fields, uppercase F and uppercase G. They have domains that include an oriented smooth curve C. Oriented means there's a direction to travel along. Smooth means that r prime of t is not 0. If we want to find the vector line integral of the sum of the vector fields f plus g with respect to the vector differential dr, we can instead compute f dot dr over the curve C and add the integral of g dot dr over the curve C. In other words, we still have a sum and difference rule for vector line integrals. What if we multiply our vector field by a constant before we dot it with the dr differential? In this case, it doesn't matter, just as it didn't matter in a scalar line integral. We can pull the constant out of the vector line integral. The third property is one that is unique to the vector line integral when compared to the scalar line integral. In a scalar line integral, we were computing the area of the drop curtain, which means it has to be non-negative. It doesn't matter which way you travel along the curve, the drop curtain is the same. However, for a vector line integral, the direction of travel does affect the value of the vector line integral. If you evaluate the vector line integral of f dot dr along negative c, going in the opposite direction to the orientation, you get negative times the vector line integral of f dot dr on regular c. The last one is the one that refers back to what we just defined with piecewise smooth curves. And it says, suppose that you have a piecewise smooth curve in the domains of both f and g, and your curve is the sum of the piecewise smooth sections, but each section itself is smooth, such that the endpoint of one c sub I is the beginning of the next curve section, c sub I plus 1. Then to find the vector line integral f dot ds along this, that should be f dot dr, along the curve gives us f dot dr on c1, c2, all the way up to c sub n. So I've fixed my notation so that f dot dr, the integral along the curve C, can be found by computing f dot dr on each of the piecewise smooth sections and adding all of them together. Let's now turn our attention to example 7. In example 7, we want to calculate the vector line integral of f dot dr, where f is the vector field given by y squared, comma 2xy plus 1. And C is a triangle with vertices at the origin 4, 0 and 0, 5, oriented counterclockwise. Now, one of the things to note about this is because it is a triangle, it has 3 corners. And because it has 3 corners, it is not completely smooth. We will be able to label the 3 line segments as C1, C2, and C3. And as long as we stay on each line segment, the line segment itself is smooth, but it is not smooth at the joins of the line segments, at the vertices. It doesn't really matter which point we start at, 0, 0, 4, 0, or 0, 5, as long as we go around the triangle one time exactly, and we go in a counterclockwise direction. Remember that you can always parameterize a line segment by writing r of t as x naught times the quantity 1 minus t plus x1 of t, comma, y naught times quantity 1 minus t plus y1 of t, where we're moving from x naught, y naught to the point x1, y1. Go ahead and pause the video to parameterize the 3 separate line segments in whatever fashion you choose, then turn the video back on so we can compare parameterizations. So let's take a look at the parameterizations. There are infinitely many ways to parameterize a line segment, but 2 obvious ones are to let x be t on the horizontal line segment between the origin and 4, 0, and to set y to be 0. Then t would vary between 0 and 4. You could also use the formula that we gave above for representing a line segment between point x naught, y naught and point x1, y1, where t varies from 0 to 1. Applying that formula, we get the parameterization 4t comma 0, but t varies from 0 to 1. You can use either one, the result will be the same. For the second piecewise smooth section, which was a slanted line, I chose to use the formula, and I got the parameterization 4 minus 4t comma 5t between 0 and 1 for t. On the third section, it is tempting to want to let y be t and x be 0, but the problem is that that would graph it in the reverse direction. which is fine as long as you remember to change the sign of the vector line integral on that particular section. Instead, I went ahead and did the counterclockwise parameterization using the formula and got 0, 5 minus 5t between 0 and 1. The next thing we need to do is we need to find r prime of t and f of r of t. R prime of t will be different for each of the 3 different parameterizations, and f of r of t will be different for each of the 3 different parameterizations. Pause the video to write down the derivatives with respect to t of each of the parameters, and then turn the video back on so we can compare. Let's take a look now at the derivatives. The derivative of R1 turns out to be 1, 0, where I use the parameterization t, 0, where t varies from 0 to 4. R2, when I took the derivative with respect to t, gave me -4, 5, and t is varying from 0 to 1. When I took the derivative of the third parameterization, I got 0, -5, t varying from 0 to 1. To help organize our information, I've created a table and copied the information we have so far into the table. The next thing we need to compute is f of r of t on each line segment before we find f of r of t dotted with r prime of t and multiply by the differential dt. To find f of r of t, we have to know the vector field representation, which is y squared, 2xy plus 1. And we're going to replace the x and the y with the corresponding component from the parameterization. Go ahead and pause the video to compute f of r of t for all 3 parameterizations. For the first parameterization, R1, we replace x with t and y with 0 in the representation of the vector field, which is y squared, 2xy plus 1. When we replace these, we end up with the vector 0, 1. In the next case, we're taking R2, the second parameterization, and we're replacing x with 4 minus 4t, y with 5t. So we square 5t, 2 times the 4 minus 4t times 5t, and then add 1 to get f of r of t for the second parameterization of 25t squared, 40t minus 40t squared plus 1. Our final parameterization, when we substitute 0 for x and 5 minus 5t for y, gives us 5 minus 5t squared, 2 times 0 times quantity 5 minus 5t, and then we add 1. This gives us 25t squared minus 50t plus 25, 1 for f of r of t in the third parameterization. In order to compute f dot dr, we need to go ahead and find f of r of t dotted with r prime of t. If you have space on your page, you can go ahead and compute it directly below. Pause the video while you compute f of r of t dotted with r prime of t for each of the 3 different parameterizations. When we compute f of r of t dotted with r prime of t from the first one, we're going to get 0, 1.10, which gives us 0 plus 0, which is 0. The middle one is the one that is the most difficult. We have f of r of t, 25t squared, 40t minus 40t squared plus 1, dotted with -4, 5. This gives us, when we simplify, -300t squared minus 200t plus 5. The final one, when we compute f of r of t dotted with r prime of t, gives us f of r of t, 25t squared minus 50t plus 25 comma 1, dotted with 0 comma negative 5. The first components go to 0. The second multiplied together give us negative 5, giving us f of r of t dot r prime of t to be negative 5. Finally, to find f dot dr on the entire curve, which is the triangle from 0, 0 to 4, 0 to 0, 5, and back again to the origin, means to compute the vector line integral on each piece and then to add the results together. What we want to do next is go ahead and write down the integrals that we have to compute. Our first one gave us 0 for the integrand, so we can ignore the contribution of the first part of the curve, C1. Then we need to integrate for the second one. Note that the second one has limits of integration from 0 to 1. Be careful, because if you parameterize differently, you may not have the same limits of integration. Let's go ahead and write down the next vector line integral. We're going to be integrating, and I suppose I should keep it color-coded, the integral from 0 to 1 of negative 300 t squared plus 200t plus 5 with respect to t. And then for the last one, it also goes from 0 to 1, but our integrand this time was negative 5 with dt. Go ahead and pause the video to work this one out, then turn the video back on and we'll compare our results. When we integrate over C2, we find that we end up with negative 300 t cubed over 3, which reduces to negative 100 t cubed. When we substitute the limits of integration, we get negative 100. The second term, 200t, integrates as 200t squared divided by 2, which becomes 100t squared, which when we substitute limits of integration gives us plus 100, which cancels the first term. The last term, 5, when integrated, gives us 5t, evaluated from 0 to 1, which gives us plus 5. When we integrate over the third piecewise smooth component of the curve, we have the integrand negative 5, which gives us negative 5t, or negative 5 when evaluated between 0 and 1, which means that, in fact, our net vector line integral gives a value of 0. We're going to find in the next section that this is a common occurrence when you have what's called a conservative vector field and you evaluate it on a closed curve where you begin and end in the same location as we did on the triangle. The next thing we want to look at are some of the applications of vector line integrals. We're going to start by discussing what's called flux. Flux is used in applications to measure the amount of fluid flow across a curve. Let's go ahead and draw a curve up here so we can think about what is happening. When we talk about flow across a curve, we're talking about not going with the curve, but going across the curve, like this. In this sense, we're trying to figure out how much of the vector field lines up, in a sense, with the normal vectors to the curve. The idea of flux is very important in Green's theorem, which is one of the major theorems in calculus. It also applies to higher dimensions for Stokes' theorem and the divergence theorem, which are covered in 3 of the sections remaining in this chapter. We'll take a brief look at flux here, but it's going to come back again later on. When we think about flow across a curve, we want to differentiate this from flow along a curve. If we're thinking about flow along a curve, then we're thinking about how the vector field lines up with the curve so that the flow is moving along the curve, along the tangent vector, as in the blue arrows that you see here. When we're looking at the flow along a curve, we're looking at f dot the tangent vector ds, the vector line integral along the curve, where t is that unit tangent vector, and ds is the arc length differential. When we're talking about flow across a curve, however, we're not talking about going along the curve. We're talking about moving normal to the curve. It makes sense then that the change we make in the vector line integral is to replace the unit tangent vector with the unit normal vector. You can think of this sort of as a membrane in the flow of some fluid. The membrane doesn't impede the flow of the fluid at all, but we're measuring the flow directly across or through the membrane. When we do this, we find the vector line integral of f dot a unit normal vector with the arc length differential on the curve C, where C is a smooth curve. Since we know that the unit tangent vector and the unit normal vector are perpendicular to one another, this makes the vector line integral of f dot the tangent vector ds and the flux integral f dot a unit normal vector ds also perpendicular to each other. Let's go ahead and look at another picture of what we're talking about. When we're talking about moving across a curve, we're talking about the flow of the vector field aligned up with the normal vector to the curve, pictured in the image on the right with the green normal vectors. With the curve on the left, the normal vector is pictured here in blue. The vector field is flowing in this direction, but we want to measure how much of it is aligned with the normal vectors as it flows across the curve. The formal definition of flux, then, is the quantity of fluid flowing across the curve per unit time, or the rate of flow. It's calculated with a line integral of the vector field dotted with a unit normal vector with the arc length differential ds. To find a unit normal, we simply have to find any normal vector and divide by its magnitude to get a unit normal vector. Let f be a vector field and let C be a smooth curve with the parameterization x of t, y of t, where t varies from A to B. We're going to choose a random normal vector to be y prime of t, comma, negative x prime of t. The flux of the vector field across the curve is the vector line integral f dot a unit normal vector ds over the curve C, which is the same as the single integral from t equal a to t equal b of f of r of t dotted with a normal vector dt. Let's take a look now and think about why this particular normal vector, y prime of t, negative x prime of t, is in fact normal to what we have. If we think about it this way, know that a tangent vector would be taking r of t and taking the derivative. It's not the unit tangent vector, but it's a tangent vector. So that a tangent vector is given by x prime comma y prime. We know from the definition of the dot product that when they are orthogonal or perpendicular, the dot product will give us 0. And when the dot product is 0, they must be orthogonal. If we dot the normal vector with the tangent vector r prime, we find that it does give us 0, which means that this vector, y prime of t, negative x prime of t, is in fact a normal vector to the curve. It's not the only normal vector, but it definitely is one that will work. Let's take a look now at example 8, where we want to calculate the flux of a vector field x plus y comma 2y across a line segment going from 0, 0 to 2, 3, where the curve is oriented from left to right, so from the origin to the point 2, 3. We're going to follow through our steps by first parameterizing our curve. Then we're going to rewrite the vector field in terms of the parameterization f of r of t. Our next step is to find a normal vector and then compute f of r of t dotted with the normal vector, and to integrate this between t equal a and t equal b. Go ahead and pause the video to work this one out, and then turn the video back on so we can compare our results. To find the flux, we first need to parameterize the curve, which is the line segment from 0, 0 to 2, 3. I used the formula x naught times 1 minus t plus x1t, comma y naught times 1 minus t plus y1t to parameterize the line segment. Since my initial point, x naught, y naught, is 0, 0, and my final point, x1, y1, is 2, 3, this gave me 2t, 3t for the parameterization for t between 0 and 1. The next thing I want to find is f of r of t for that parameterization, where I replace x with 2t and y with 3t. My vector field is x plus y comma 2y. So x plus y gives me 2t plus 3t, or 5t, for the first component, and 2y, or 2 times 3t, or 6t, for the second component. Now, if I were finding the vector line integral, I could dot this with r prime of t and compute, but I'm looking for flux. So I need a normal vector, not a tangent vector. So what I do instead is I compute a tangent vector, which is the derivative of the parameterization. This gives me 2, 3 for a tangent vector. Based on the tangent vector, I swap the components and negate the second to get a normal vector of 3, negative 2. Now, to find the vector line integral giving me the flux, I go ahead and find the dot product of 5t, 6t with 3, negative 2, which ends up giving me 15t minus 12t, or 3t. When I integrate 3t, I get 3t squared divided by 2, evaluated between t equals 0 and t equal 1. This gives me the flux, or the flow, across the line segment of 3/2. We can look at this out here on CalcPlot 3D, and we can see that near this line segment, the vector field is actually flowing with the curve, not across the curve. For this reason, it's not surprising that our flux value is relatively low. There is an alternate notation for the flux integral. If we represent the vector field as PQ or PQR, then we can write the flux as f dot the unit normal vector ds as p of x and y, q of x and y, dotted with the normal vector dy comma negative dx. This gives us p dy minus q dx, or if you want to integrate with respect to x first, negative q dx plus p dy. This is integrated along the curve, and in order to do that, we write it in terms of the parameterization. Negative q of r of t times dx dt plus P of R of t times dy dt, integrated with respect to the differential dt. Again, Q is the second component of the vector field with the parameterization substituted inside. Dx dt is the derivative of the first component of the parameterization. You can apply this formula to the previous problem we did, and you will find that you get the same result, 3/2, for the value of the flux integral. We have one last topic to discuss, which is circulation. We've already actually computed a circulation when we computed the vector line integral around the triangle. Circulation characterizes many gradient fields, in other words, conservative vector fields in terms of line integrals. There's a strong relationship between being a conservative vector field and the value of the circulation. We'll see this coming up again and again. Remember that to be a gradient vector field or a conservative vector field, there is a function, lowercase f, such that the gradient of f, del f, is equal to the vector field. We call them conservative because they model physical systems in which energy is conserved, such as gravitational fields and electrical fields. When we define the circulation of a vector field, we're defining it along a closed curve, like that triangle that we did earlier, where you begin and end in the same location. For the circulation integral, you'll notice that we've added a circle into the center part of the integral to indicate that it is on a closed curve. That indicates that it must be the circulation integral. There are times, however, when we drop the circle simply because we forget. So just because it's not there, if it is a closed loop, it does represent circulation. It is the vector line integral formula that we were using earlier in this section, with the added part that it has to be on a closed curve. It's simply f of r of t dot r prime of t dt on a closed curve. We're going to discover in the next section that if the vector field is conservative, then evaluating this on a closed curve will give us 0. Let's go ahead and think of this as a velocity vector field for some fluid, where the vector at each point represents the velocity of the flow at that point. And we're going to allow C to be an oriented closed curve. At a particular point on the closed curve, which is going to be represented by some kind of loop, and we're looking at point P, the closer the direction of the velocity vector from the vector field is to the direction of the unit tangent vector at P, the larger the value of the dot product between the two. We know from the definition of the dot product that u dot v is equal to the magnitude of u times the magnitude of v times the cosine of theta, that the cosine of theta reaches its maximum value of 1 when theta is 0. So the closer that the vector field aligns with the direction of the tangent vector, which is pointing in this direction, then the larger the value of the dot product. And again, recall that our vector field can point in different directions at different points. What we're wondering is, how well does it align with the orientation of the curve? We'll get the minimum value when it moves in the opposite direction, when theta is equal to pi. So the value of the circulation can be found by taking the velocity vector field composed with the parameterization r of t and dotting it with r prime of t dt, measuring the tendency of the fluid to move directly along the curve in the direction of the orientation. Let's take a look at example 9. In example 9, we want to calculate the circulation of a vector field given by negative y divided by x squared plus y squared, comma x divided by x squared plus y squared, along a unit circle oriented counterclockwise. We know a circle is a closed curve because you get back to where you started when you travel all the way around. In order to compute this, we want to parameterize the unit circle. In this case, notice that it doesn't matter where we begin and end. We can use a normal parameterization for the unit circle. Then we want to compute f of r of t and r prime of t, dot the two together, and then evaluate the integral between t equal a and t equal b. Go ahead and pause the video now to work this out, then turn the video back on so we can compare our results. For this problem, I chose to parameterize the unit circle as cosine t sine t for t between 0 and 2 pi. Then I computed r prime of t as negative sine t comma cosine t. Then I need to parameterize the vector field by substituting x for x cosine t and substituting sine t for y. This gives me negative sine t over cosine squared t plus sine squared t, which becomes 1, giving me negative sine t for the first component. The second component gives me cosine t over cosine squared t plus sine squared t, which again is 1 by the Pythagorean identity, and the second component becomes cosine of t. Once I have that, I dot that vector with r prime of t, a tangent vector. This gives me sine squared of t plus cosine squared of t, which again is a Pythagorean trig identity, giving me 1. When I integrate 1 dt, I get t evaluated from 0 to 2 pi, or the value of the circulation of the vector field to be 2 pi. This is the tendency of the fluid to flow along the curve, which is the unit circle. We have one last example to take a look at. This is example number 10. In example 10, we want to calculate the work done by a vector field given by 2x comma 3y on a particle that traverses the unit circle counterclockwise. We want to assume this time that the particle begins its movement at negative 1, 0. We can think of the circulation around a closed loop as the amount of work done by a force on a particle and moving it around that closed curve. Since we again have the unit circle, we're going to go ahead and use cosine t sine of t as the parameterization. But in order to force it to start at negative 1, 0, we're going to have to start at some place other than 0 to 2 pi. If we want to begin and end here on the negative x-axis at negative 1, 0, we could start at pi and travel to 3 pi, or we could start at negative pi and go to pi. In order to compute the circulation, we need to find f of r of t dotted with r prime of t, and then integrate with respect to dt. Pause the integral to work it out now. Since our parameterization is cosine t sine t, the derivative becomes negative sine t cosine t. Then we can compose the vector field with the parameterization f of r of t, replacing x in 2x with cosine of t to get 2 cosine t, and replacing y with sine of t in 3y to get 3 sine of t. Then we take the dot product of f of r of t with r prime of t, which gives us sine t cosine t for the new integrand. The integral around the closed curve C of f dot the unit tangent vector ds becomes the single integral from t equal pi to 3 pi of sine of t cosine of t dt. I do a u substitution, allowing u to be sine of t, so that du is cosine of t dt. When t is equal to pi, the sine of pi is 0, so the new lower limit of integration is 0. However, when t equals 3 pi, the sine of 3 pi is still 0, so the upper limit of integration is also 0. When we integrate from a constant to the same constant, we end up with 0 area, which gives us the value for the circulation to be 0 around this closed curve. This is the end of the second video over section 6.2 on line integrals. In the next section, we'll take a look at conservative vector fields, also called gradient vector fields, and their special relationship to vector line integrals. See you soon in the next video.